In this particular question, we've been presented an unidentified compound and we've been told it contains carbon, hydrogen, and nitrogen. And we've been asked to work out the empirical formula. So in approaching this question, one of the first things I'm going to do is I'm going to do a quick check and see, well, these percentages by mass which we've been given, what's the total, what does it add up to? And I would invite you to have a go at that and see what you get. In this case, we've got 45 plus 2.5 plus 52.5. And what we get is, well, if you have a go, you find that comes to 100. Now, what we're trying to do is we're trying to work out the simplest whole number ratio, right? So that's the empirical formula, the simplest whole number ratio between the elements present in this particular compound. Now, in order to solve for that, what I'm going to do is I'm going to make an assumption. I'm going to assume, for the purpose of solving that actually, let's assume that this particular sample I've got is a total of 100 grams. What that's going to enable me to do is going to enable me to solve for the amount of substance, right? Because if we've got a mass, we can now use the equation of moles N equals mass divided by molar mass, right? To solve for the equation. Okay, so given that, what I'm going to do now is based on that assumption, this is going to be 45 grams, 2.5 grams, 52.5 grams, okay? And that is for carbon, hydrogen, and nitrogen. Right, so in order to use this equation, I'm going to need the molar masses, which you may know the molar masses of these elements, but even if you don't, you can just use the periodic table, right? So I'm going to refer to the periodic table to get the molar masses, which is effectively the relative atomic masses, right? So here we have hydrogen, nitrogen, carbon, right? So, and I've just got them here as well. So for the molar mass of hydrogen, that's going to be 1. So I'm just showing my working here, right? Just to show that my thinking on paper. The molar mass of carbon is going to be 12. And the molar mass of nitrogen, which as you can see here is going to be 14. So I'm going to effectively, and all of those are in effectively grams per mole, right? So at this stage we're using grams per mole. So what I'm simply going to do at this stage is to get to the moles is divide each of these by their respective molar masses. So that's effectively going to be 45 divided by 12, because that's a carbon, 2.5 divided by 1, 52.5 divided by 14. Right, so have a go, see what you get when you calculate those. And if you do that, what you should find, for 45, you divide it by 12, you're going to get 3.75. For hydrogen, I mean, you don't need a calculator really to work this out, because you're dividing by 1. It's just going to give you 2.5. And for nitrogen, so that's 52.5 over 14. That's going to give you actually 3.75. So we can already even at this stage infer that probably the amount of substance with respect to carbon and nitrogen, the number of atoms of each element that would be represented in the empirical formula would be the same as each other. But at this stage, we still don't have a whole number ratios, right? We have all these decimals, and they're not necessarily easy to just round. They're not super close to any particular whole number. So at this stage, because of that, what I'm going to do is I'm simply going to divide all of them by the smallest value, so that at least one of the values would be an integer, right? So I'm going to divide everything by 2.5, right? So the smallest is 2.5. So I'm going to divide everything by that. So if we do that, 2.5, right? So if you do that, you should get a new ratio, and with that new ratio, you're going to have effectively 1.5, 1, 1.5, right? And at this stage, it should be, maybe it may seem fairly clear what this might lead to as far as the ratio, the final ratio that we'll use for the actual empirical formula. But in any case, what we're doing at this stage is effectively a scale up. So we're going to consider, well, we'll start with 2, but we'll progressively, if needed, progressively go up, multiply it by everything by 2, by 3, by 4, etc. Okay, which one leads to the smallest whole number ratio? Now, in this particular case, and you can kind of determine that from visual inspection as well, just because you've got the 0.5, but in this case, simply multiplying it by 2, by multiplying every value by 2, gives you a whole number ratio. So if we divide this by 2, so I'm just going to put this in brackets, divide by 2, did I say divide by 2? I meant multiply by 2. So if you multiply everything by 2, you get your simplest whole number ratio. So 1.5 you get 3, 1 you get 2, 1.5 you get 3, right? So at this stage, this is, as we've done that times 2, effectively we now have 3, 2, 3, which if you look at it, well, what if we divide it by 3, we're not going to get a whole number ratio anymore. Divided by 2, the same thing. So this would be our simplest whole number ratio, right? And therefore associated with the carbon would be a 3, associated with the hydrogen would be a 2, associated with the nitrogen would be a 3, right? Okay, and in terms of, well, obviously putting this together, therefore we'd get C3H2N3, right? And so in this particular case, this is our empirical formula. This would be the simplest whole number ratio between the elements there. So yeah,